Hello, everyone. I'm Kuratulayan Ali, a PhD researcher working at the University of York. I'm glad to be here presenting in an in-person conference for the first time. So today I'll be talking about our work on selective traceability for rule-based model-to-model transformations. So the outline of today's talk is going to be, I'll start with the background, a little bit context to my work, and then we'll talk about the problem statement and what actually motivated us to do this work. And then I'll talk about the approach briefly. I guess again.
It might be your parent. Or change. The other thing we can do is just change to this microphone.
Yeah, I guess
because this is not that. You want to take it off?
Yeah, I guess let's use that.
Sorry about this.
No worries. So do I need to set it up or?
You can just speak into it.
Hello.
Also,
Yeah, I guess.
Yeah. Exactly.
Perfect. All right. So then I'll talk about the proposed approach, and then I'll walk you through some experimentation and the results, and then finally I will conclude. So to put the work in the context, in model-driven engineering, usually we have several activities such as like code generation, model-to-model transformation, model validation. So one of the very common activities that we do in MDE workflow is the model-to-model transformation. So we often need to map one source model to another target model. So we have several languages to write model-to-model transformation, such as Epsilon's transformation language, ATL, YAMTL, etc. Here in this work, I'll be talking about Epsilon, and the reason for using Epsilon is it's very nice, flexible approach with the different modeling technologies such as EMF, Simulink, etc., through the Epsilon model connectivity layer. And then we have several languages dedicated for the specific tasks like model-to-model transformation, code generation, etc. And all of them basically extends the core Epsilon language, which is the Epsilon object language. So here in this work, the main language of interest is the ETL, which is the Epsilon Transformation Language. I'll just quickly talk about it, that how it works. So as you can see, this is a program written in Epsilon's transformation language. It's a rule-based model-to-model transformation language. We can have one or more input models and then transform them to one or more output models. So we can have optional pre and post blocks. So pre blocks are executed before the execution of the transformation rules, and post blocks subsequently after the transformation rules. One important thing to note here is the source element resolution. Often we encounter in model-to-model transformation that we need to get the elements that are created or generated by another rule. So there are statements such as equivalent or equivalence to return the elements. For instance, here in this line, this a dot movies dot first dot equivalent is actually returning the elements that are created by this movie rule. So for this, we need to keep a transformation trace to see that which source elements are actually transformed to corresponding target elements. So epsilons basically keep a trace of all the source elements that are transformed to the corresponding target elements. Now, the problem or the motivation for this work is that when we talk about models of like increasing size, so often we'll see that in MD we have like very large scale models like models that are in order of millions of elements. So when the size of the model is increased, the transformation trace would be populated proportionally. So which would not be very efficient, both in terms of memory footprint and also in terms of execution time. So the idea here is to make it scalable, to make more efficient use of the resources, because we have these tailored model transformation languages. They are really nice for the task that they are targeting, but the performance is a major bottleneck. So what we have proposed in this paper is basically the contributions are divided in two parts. So the first thing is to reduce the memory footprint. What we propose is to have a transformation trace which is selective. So we don't keep all the source target element pairs. We just keep the ones that are needed elsewhere in the transformation. So we just end up getting the absolute necessary selective trace. And the second contribution of this work is to rewrite the transformation, because it's a rule-based transformation language, as I mentioned, into imperative form, where we convert the rules to operations, and then we change the equivalent calls to the corresponding operations, so that program during the execution should not do this resolution itself. So we do everything before the execution of the program. One important thing to notice here is that we do not sacrifice any expressiveness of the language. So we still keep the benefit of the interpreted language, that is ETL. So we don't rewrite or desugar down it to Java program per se. Let's say. So the approach here is illustrated. So we, in the first step, as you can see, we have a static analyzer, which basically gets the transformation script, the source meta model, and the target meta model, and then we get a type resolved AST. I'll talk a bit in detail later. And then we have a dependency graph generator, which generates a dependency graph, which is the input to the rewriter, and then the rewriter will give us a rewritten transformation, which will then be executed by the ETL engine, and then we will get the output model, which would be the same as we would get by the normal ETL execution, but with the selective transformation trace, not the whole transformation trace. So static analyzer, how it works is that so in static analyzer, basically we have a visitor that visits different parts of the AST, abstract syntax tree, and then using the meta model connectivity and the type inference and type resolution, it gives the type resolved abstract syntax tree. What I mean by type resolved abstract syntax tree is the same abstract syntax tree, just populated with the type information. So for example, if we have this rule here, so if we want to see the types of the various constructs, it would be, for instance, a dot is many is a Boolean property, so the type would be resolved to Boolean. And then in similar way for name to string. And then, for instance, c dot table would be a model element type table of the model target. So with this type information, now how we use it in the next steps, let's have a look. So in the dependency graph generator, as I mentioned, what we do is, so we have a program written in Epsilon's transformation language here. So what we do is we look for the equivalent calls. So equivalent calls are basically resolving elements from the other rules. So using the static analyzer, we analyze that when, for instance, it's in this line, it's c dot table a dot owners dot equivalent. So we know that this rule is basically calling elements from the class to table rule. So what we do in the dependency graph is create nodes with all the rules. So as you can see, these are the rule names, and then we create an edge if there is a dependency between them. So for instance, in rule single valued attribute to column, we see that there is a dependency to class to table rule, so we create an edge here. Now with this information, we know that which rule needs the traces of which other rules. Now, finally, in the Step 3, rewriting. What we do is we transform rules to operations. As I mentioned, the second contribution of the paper is to desugar the ETL transformation to the imperative program. And then the main thing why we are transforming rules to operation is to replace equivalents to the corresponding operation calls. So the program doesn't have to do it at the execution time. And then we create maps for keeping selective traces. Excuse me. Right. So after the rewriting is done, now it comes to the execution. So in execution, we use the normal ETL engine, just with one difference. When we resolve the operations, it can be a very expensive process because it uses the Java reflection API. So we use static analyzer to basically say that, for instance, if it's an operation class to table, using static analyzer, we resolve the operation calls before the execution of the program. So when the program is actually executing, it doesn't take time for this operation resolution. So how we evaluate this approach is, so if you look at the same diagram that I showed earlier. So for the model to model transformation, we use the object oriented to database transformation. And for the source models, we use synthetic models generated ranging from 10,000 model elements to 25,000 model elements. And then we evaluated it using the normal ETL, YAMTL, and ATL to compare our approach with the other state of the art. Uh, One important thing in the experimental setup is this, because I mentioned we are rewriting the transformation, it's important to preserve the semantics of the program. So we use EMF compare to measure the correctness, so that the rewriting that we do, it doesn't change the semantics of the original transformation. And then for the internal evaluation, I compared it with ETL, the optimized ETL compared with ETL. But for the external evaluation, we use ATL and YAMTL. The reason for using these two languages is that ATL is a very widely used, interpreted transformation language, while YAMTL is a compiled transformation language. So it was interesting to see how our approach performs in comparison with these languages. So for the internal evaluation, as you can see, here is the execution time. Because we did everything before the execution of the program using the static analyzer. So the execution time has decreased for the optimized ETL. And then in the same way, because now the selective trace is much smaller compared to the original transformation trace, we end up consuming less memory compared to the normal ETL. Similarly, in the external evaluation, we see that YAMTL outperforms in terms of time. This is because YAMTL is a compiled language and it compiles down to Java. So the execution is much more faster, but because it's incremental and because it's incremental, so it uses a lot of cache space. That's why you see that it ends up consuming the most memory here. So these are some results that we got by comparing our approach with the other state of the art. So to conclude, I presented the approach for optimizing model-to-model transformations that uses static analysis and dependency graph and the program rewriting techniques. And I've shown you how the experiments deliver significant performance improvements in terms of memory and the execution time. Um, in the further iteration of this work, we plan to work on optimizing at the expression level, because right now the optimization that I mentioned are all on the rule level. So we can optimize the expressions to optimize the overall model-to-model transformation program. And the another interesting thing could be to dispose the selective traces when they are no longer required in the program, so that at the end we end up with a completely null transformation trace. And then it would be interesting to see how this model to model transformation optimization performs on the other modeling technologies such as Simulink and repository based models. That's it from my side. In paper, you can find the algorithm on the extraction of dependency graph and the rewriting or desugaring the transformation, and more details and a detailed running example. So I'm happy to take any questions that you have.
Thank you very much.
Thank you.
Any question or comment?
I have two questions. I'm going to start with one.
Mhm.
You're using static analysis and
Mhm.
dependency graph, and you are obtaining some good results. Do you think it is due to some of these things, or the three of them equally, or do we have to consider them as a whole, or what do you think of these things is having more impact on the improvement of the results?
Right. So basically, static analysis, as I would call it, it's very fundamental. So, for instance, you cannot get a dependency graph without static analysis. So I would say static analysis and dependency graph are the foundational work that we cannot really separate to get this performance benefits. But on the other hand, obviously, the end result is due to reducing that transformation trace. But it's really dependent on the analysis, which is quite fundamental. And obviously, this analysis can be used for lots of other things as well. So, yeah, that hope I answered.
Yeah. Can I ask one question? And my second question is related to the static analysis. Because how does it compare to, for instance, an analyzer that
Mhm.
is created for ATL? Is it the same for ETL, or is it different somehow?
Mhm. Basically, the ATLizer is the static analyzer for ATL. So wouldn't be wrong to say that this one is the static analyzer for ETL, because it's language specific. But the basic phenomena is similar. The analysis, because again in ATLizer they're resolving the types, because that type information can help us doing lots of optimizations. But there are some features of ATLizer that yet the static analyzer of Epsilon doesn't support. So we build it basically based on different. So because Epsilon has a this framework of languages, so we basically created from EOL and then extended for whichever language we are using to perform some optimization. But yeah, basic phenomena I would say is similar, because it's resolving types and stuff like that. Yeah.
Thank you so much.
Yeah.
So, other question.
I could have one. I'm just wondering if this approach can also work in programming languages, or this code, we have code as
So you mean the general purpose programming languages?
Yes, having a piece of code written
Eh,
in Java, for example, and then you can
Mhm.
translate it in another language. Or,
Yeah. So basically, the compiler optimization, I guess, is pretty much things like this, because it's a part of it's a small part of optimization. So because this approach that I mentioned in particular is for the interpreted languages, but if you have a static analyzer for a general purpose language such as Java, then there are these sort of optimizations that you can make in the general purpose languages as well. But um, I mean, my idea is that general purpose languages are already very very efficient, because they're compiled down. So I'm not sure if they would benefit the same as we can benefit in the interpreted languages with these sorts of optimizations.
thank you.
Any other question? So how about the remote side? No questions? Question?
All right. Thank
Thank you
you.
very much.
Thank you.